Welcome to the world of basic tropical geometry. In this presentation, we will explore the fascinating field of tropical geometry, which can be described as MIM plus algebra, piecewise linear shadows of algebraic geometry. It is an area where algebraic geometry meets combinatorics through tropical mathematics. So let's embark on this journey to understand the basics of tropical geometry. At the heart of tropical geometry lies MIM plus algebra. This algebraic structure redefines the conventional operations of addition and multiplication. Tropical addition is equivalent to taking the minimum of two numbers. Given two numbers x and y, the tropical addition of x and y, denoted as x circled plus y, results in the minimum of x and y. Tropical multiplication, on the other hand, corresponds to the sum of two numbers. So the tropical multiplication of x and y, written as xy, gives x plus y. These redefined operations form the foundation for analyzing piecewise linear structures in tropical geometry. Tropical polynomials are piecewise linear functions. These are formed by taking the minimum of linear functions. Consider a function p of x. P of x equals the minimum of the following set of linear functions: 3 times x plus a, 2 times x plus b, and x plus c. Here a, b, and c are constants. The graph of this function will consist of different line segments, each corresponding to one of the linear functions, with the function value at any point being the minimum of the values of the individual linear functions at that point. Here are a couple of examples to illustrate tropical polynomials. First, let's consider a univariate example. P of x equals 3x squared circled plus 2x circled plus 5. Remember that in tropical algebra, the square of x means x plus x, and the addition sign actually means the minimum. Therefore, the expression is equivalent to the minimum of 2x plus 3x plus 2, and the number 5. Now let's consider a bivariate example. Q of x, y equals x circled plus y circled plus 0. Which means that it is equivalent to the minimum of x, y, and 0. Tropical geometry finds applications in diverse fields. Let's highlight two key areas. Firstly, transportation networks. It can be used for optimizing departure times and solving scheduling problems. Secondly, financial markets. It is useful in auction design and currency trading optimization. These applications showcase the versatility and practical relevance of tropical geometry in addressing real-world challenges. One significant application of tropical geometry is in transportation network optimization. Consider the airport transfer problem. The earliest departure times for connecting flights can be determined using tropical linear equations. For example, b1 equals max of x subscript alpha plus d subscript alpha plus a subscript alpha alpha, x subscript beta plus d subscript beta plus a subscript alpha beta. b2 equals max of x subscript alpha plus d subscript alpha plus a subscript beta alpha, x subscript beta plus d subscript beta plus a subscript beta beta. These equations can help optimize the scheduling of flights to minimize transfer times and improve overall network efficiency. Tropical geometry also finds applications in auction design, particularly in product mix auctions. Bidders can express their preferences as price vectors with associated quantities. For example, a tropical bid could be represented as 60-50, 1, 90-25, 3. This notation indicates different price points for varying quantities of goods, enabling competitive equilibrium analysis. By leveraging tropical geometry, auction designers can better understand bidder behavior and optimize auction mechanisms for efficiency and fairness. Tropical geometry provides tools for analyzing competitive equilibrium, particularly in the context of indivisible goods. A key existence condition is: equilibrium exists if and only if the determinant of V belongs to the set containing -1, 0, and +1 for all subsets V of demand vectors. This condition implies that unimodular demand types, which ensure that the determinant of any subset of demand vectors is either -1, 0, or +1, guarantee competitive equilibrium existence for indivisible goods. This result has implications for mechanism design and resource allocation in various economic settings. Let's illustrate the concept with an example of an indivisible goods market. Consider a scenario with two players, A and B, each having a budget of 1. There is a single indivisible good valued at 1 by both players. In this scenario, no equilibrium exists without budget perturbation. This example highlights the challenges in achieving equilibrium in markets with indivisible goods and the need for mechanisms like budget perturbations to ensure fair allocation. To address the issue of equilibrium existence in indivisible goods markets, a generic budget solution involves budget perturbation. For instance, budget 1 equals 1 plus epsilon while budget 2 equals 1, where epsilon is a small positive number. With this perturbation, equilibrium exists with the price set between the two budgets, ensuring a fair allocation of the indivisible good. This approach demonstrates how small adjustments to budget constraints can lead to significant improvements in market outcomes. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.